All right, this is going to be review video number 9, reading a chemical formula. So just to start out, I want to define what a chemical formula is. It's basically an abridged version of a chemical name, and it uses element symbols and numbers to represent the composition of any particular substance. There are different types of chemical formulas that you might run into, and I'll show you a couple of variations towards the end of this video. But the four most common are going to be an empirical formula, a molecular formula, a condensed formula, and a structural formula. So elements in these formulas are going to be represented one of two ways, and you've seen those variations on the periodic table already. Either you are going to see an element that is represented by a single capital letter. So carbon, sulfur, potassium, all of those are examples of a single capital letter. Other than that, there are elements that are represented by one capital letter and one lowercase letter. So like helium or neon or lead. But you need to be careful when you're looking at these element symbols because some element symbols can look a little bit similar to one another. And the best example I can think of right now is this here. So a capital C and a capital O represents the elements carbon and oxygen. However, a capital C and a lowercase o together is just one element, cobalt. And if you see that in a longer formula, that distinction can help you identify what's there. Because if you're looking at, say, this, it's very important to understand that there's hydrogen and carbon and oxygen in this compound, and that it's not hydrogen and cobalt. And that can just help you in terms of your speed of understanding what you're looking at. The second thing about chemical formulas is that a subscript, or a tiny number at the bottom, tells you how many of something is present. And that subscript is always going to refer to the thing that's immediately before it. So looking at this example right here, we have SO4. This is a subscript, that tiny little 4. And that tiny little 4 is going to refer only to the thing immediately before it. So in this case, the oxygen. So in interpreting SO4, you would interpret that to mean that there is 1 sulfur present and 4 oxygens present in that compound. If you see parentheses in a compound or in a larger chemical equation, parentheses are going to work just like they do in math. The format is just a little bit different. So looking at this example right here, we see that there's a set of parentheses around that SO4. That set of parentheses is meant to isolate SO4 and also tell you that this little subscript right here is going to distribute to everything in that compound. So that 3 is going to distribute both to the oxygen and also to the sulfur. And when that thing distributes, it's going to multiply, just like you would see in math. If you had this, it would be 3x plus 9 if you distributed that 3. This one, we're going to distribute to, again, both the oxygen and the sulfur. So within this compound, we see that there's 2 aluminums, and that 3 gets multiplied to the sulfur. So in fact, there are 3 sulfurs in that compound, and we're going to multiply the subscripts together for that distribution. So 4 times 3 gives us 12 oxygens total within that compound. If you see an exponent within a chemical formula, those are going to be used specifically to represent the charge on an ion. So once again, you know that atoms or compounds can be neutral or they can have a charge. If a compound is neutral, you will not see an exponent. But if you do see an exponent, like if it's just a plus or a minus even, if it has a number associated with it, all of that is going to tell you the charge on that ion. So it tells you not only is that thing an ion, it has a charge, but it tells you what the charge is. If you do not see an exponent, that thing probably does not have a charge and is therefore neutral. A couple of other rules to note. Atoms that form positive ions are generally going to be listed first in a larger chemical formula. So here you can see one example. Sodium chloride is a compound made up of sodium and chlorine. Sodium is a metal. Metals tend to form positive ions, so metals tend to be listed first in any chemical compound. But it's not always metals that do this. Some positively charged things can be polyatomic in nature, like this one. This is ammonium, which is a polyatomic ion that has a +1 charge. Therefore, in the compound ammonium bromide, ammonium gets listed first. So it's just like a little rule of thumb. If you're not sure which part of a compound might be a positively charged ion or might form a negatively charged ion, that's how you tell. One more rule to note: if you see a dot in a chemical formula, what it means is that that chemical compound is probably a hydrate, like the one you're looking at here. The full name of this is copper 2-sulfate pentahydrate, so let me write that out really quickly. And copper 2-sulfate pentahydrate is basically just one compound, copper 2-sulfate, but as that thing was crystallizing and forming, a bunch of water molecules got trapped within the crystalline structure, which is what these are about. And it's not that the waters are bonded to the copper or the sulfate, they're just trapped in the middle of the bigger crystalline structure. So think of like salt crystals and stuff like that. A bunch of sodium and chloride atoms will link up together to form salt crystals, just like all of these link up to form copper sulfate. And in the middle of all that space, we got a bunch of water molecules trapped there that are not technically part of the compound, but they're interacting with it anyway because they're trapped in that structure. And so that's why you're seeing this little dot in the middle. It's to say, hey, water's there, but it's not actually bonded to the copper 2-sulfate. And so that's really what hydrate is. So I mentioned at the beginning of the video that there were different types of formulas you could see. And this diagram right here kind of represents the different options that you could have. And we're going to look at it through the lens of butane, which has the formula C4H10. So 4 carbons and 10 hydrogens within that compound. The first type of formula that I want to talk about that we're going to actually get into a little bit more in a bit is empirical formulas. Empirical formulas are not accurate in terms of what all is in that compound. Rather, they tell you a ratio of pieces of the compound. So if we were to reduce those subscripts to their whole number ratio, just like we would reduce a fraction, we would get C2H5. So the ratio of carbons to hydrogen within butane is 2 to 5. Or you could say 4 to 10 as well. It's just not the simplest whole number ratio. Molecular formulas are just the chemical formula. They tell you the exact number and the exact type of atoms that are present. So this one is probably one of the most common ones that you're going to see. A condensed formula like this is another way to write a molecular formula so that it kind of shows you the overall structure of that molecule without actually writing out the structure like you're seeing here. So we can see the different pieces of the structural formula. There are 3 of them. So on the left-hand side, you're seeing a CH3 group. That's this piece of the structural formula. Then you're seeing this CH2. Then you're seeing another CH2. And finally a CH3. So that kind of tells you how to draw out the structural formula, and that's why we used condensed formulas. You're not going to see hydrocarbons that are really long like this one, usually as a structural formula. Instead, you'll see pieces of a condensed formula called out. So like if we were doing this molecule, for example, you can represent that molecule as CH4O, or you can see it written as CH3OH. And both of these are the exact same molecule. They both have 4 hydrogens, they both have 1 oxygen and 1 carbon, but this one kind of tells you how those things are arranged, because if I draw out the structural formula like this, you can see that OH group on the end. And so that just makes it a little bit easier to draw out. So that's really the use of our condensed formulas. And then once again, your structural formula is just the whole structure. And so you'll see that one a lot too, especially as we move into you trying to draw Lewis structures of not only neutral compounds, but also compounds with charges and stuff like that. If you have any questions about different types of chemical formulas or how to interpret them, please ask.